Isn't it? No, sorry, I skipped one. Number 4 is the radiation. Again, this looks, I can tell from looking at it, it's nice. Okay. Part A1. The naturally occurring isotope thorium-232 has a half-life of 1.405 times 10 to the 10 years. Initially, the sample contains 2.25 times 10 to the 20 atoms. What is the number of atoms after 1 times 10 to the 9 years? So, this is n equals n0 e minus lambda t. The lambda is log 2 over t a half, isn't it? Yes? So, we can keep it in years. What's the time? 10 to the 9, is it? 10:10? Yeah. No. In the question, the time.
Oh yeah, 1.
Yeah. And the n0 is 1.405 times 10 power 10. So if I just plug in the numbers for n0, t, and lambda, and just hit it in on my calculator, I will get the wrong answer. Let me see. That's because I typed in the wrong n0. n0 is 2.25 times 10 to the 20. 2.25 times 10 to the 20. Now I get the right answer. 2.14 times 10 to the 20 atoms. Alright, the next part is what's the activity? Okay, what's the form of activity? Minus lambda n. Which is fine because that's minus log 2 over t to the half and 0. Now, I don't know if he uses equals or years. Now, you see, he uses equals, so it makes me feel like I should convert my time into seconds. Which I don't want to do, but gotta do what you gotta do. N0 is 2.25 times 10 power 20. I need to convert my time, my half-life, from years into seconds. So let me see, that's multiply 365 to make it days, 24 to make hours, 3600 to make seconds. And I got the activity is minus 352 equals. Although he doesn't bother with the minus, which is okay. Well, technically it's... Well, no, I guess not actually, because activity equals is destruction per second. I guess not. Do we normally use minus or not? I don't think so. No, so no minus here.
In this formula there is no minus.
Yeah. Will you tell me a minus 10? Oh, never mind. No, never mind. Right, the alpha decay of thorium releases 4.083 mega electron volts of energy. Determine the mass. Right, so they want the mass of thorium. Okay. No, what? Right, so actually I should write down what's happening. What you have here is thorium 232, and when it decays, it becomes radium 228 plus an alpha particle.
Do not write this.
No, I'm just getting a picture in my head of what's happening. So we know the mass of this. Oh, and also actually there's some energy released as well, which I'll call E. We know the mass here. We know the mass here. We don't know the mass here, and we don't know the energy. Can you see that? So if we knew the energy, I suppose we'd be finished. Now, let's call the thorium's mass we know. The thorium's mass is 232.0381 U, and that should equal the radium's mass, which we don't know, so I'll just call it X, plus the helium's mass 4.0026 U, plus the energy as if it was a mass. So you know you have the formula E equals mc squared. So if I wanted the mass here, what would it be? It would be, it'd be the energy, which we know. I wrote we didn't know the energy, but, well, we didn't know the mass that produced that energy. So it'd be E over C squared.
Formula is? What's the formula? M is equal to E over C squared.
E equals mc squared. You've seen that before. Oh, sorry, you've seen that before. Yeah. Okay, so it just seems like it's a matter of just typing in the numbers, really. But I need to work out what the E is, E over C squared is first. So E over C squared, that is 4.083 E electrons over 3 times 10 to the 8th squared. What number is the C? 28. And does the formula book tell you how much U is or not? It should do. It should tell you at the front. Is that the book value? Yeah, thank you. 1.66 times. It's small. It's small. It's small. Yeah, no, I haven't got the X yet. I'm just getting the E part. Yeah, the M. Yeah, so that comes out at being a tiny, I can't believe it, 4.3847, etc., 10 to the minus 9 U. Oh, no, it is not, because I forgot it is mega electron volts, so I need a 10 to the 6th here, which I'm missing. It is mega, isn't it? That's much better. 0.0043847 U. So then my X is correct. My X is 228.0311 U. Huzzah. Right, next part.
You don't have any formulas for this chapter in the book.
Which chapter? This one? It's really just E equals mc squared. Okay. Next is, it's assumed that the thorium atom is initially at rest and all of the energy is released becomes kinetic energy of the alpha particle. Okay, so do you see here? What they're saying is this energy here takes the form of kinetic energy of the alpha particle. They want to know how fast is the alpha particle going. So what you have here is the kinetic energy is 4.083 mega electron volts. A half mv squared is 4.083 mega electron volts. The V will be twice 4.083 times 10 to the 6 times E over the mass of the alpha particle, which is 4.0026 times U, which is 1.66 times 10 to the minus 27 with a big square root. Two times 4.083 times 10 power 6 times 23, okay, 4.0026 times 1.66 times 10 power minus 27. I got 14032,489 meters per second, and that is correct. Or if you want, you can see how fast it's going. It's going 14,032 kilometers per second. That's a fast alpha particle. Okay, in practice, the emission of the alpha particle will cause the radium nucleus to recoil in the opposite direction. Determine the resultant velocity. So what they're saying is happening here is that before the collision, before the separation, you have your where's it gone? Radium, and you have your alpha particle, and they're both at rest. And then afterwards, that will move to the left, and that will move to the right. And they say after the collision, this is going 14032 kilometers per second, although it's really not, but they said to use it. And they want to know what's the speed here. So what type of problem is this? Collision, conservation momentum. So you have m1u1 plus m2u1 equals the mass of the radium, which is what I worked out. What did I say the mass was?
What is between that
The alpha. Use the velocity of the alpha particle calculated above. What was my mass for radium? 228 point U V plus 14032,000, and do I have a mass of an alpha particle? I do. It's 4.0026 U. Now, is there a U in everything? There is. That's nice because I can cancel the U here and the U here. So I get 0 equals 228.0311 V plus 14032,000, 4.0026. So I can get my V as a negative. .6 kilometers per second, because it's going to the left.
If you don't put minus zero is now.
Yeah, because he asked for velocity, not speed.
You don't have like zero in everything. How would you solve it?
What do you mean if we don't have u?
If you.
If he still had u? We're just putting the number for u. Is that a trick question?
No.
You're trying to catch me out, were you?
No. I didn't know that.
Yeah, okay.
The 17 constant 17. Right?
I don't know, it's in the formula book. Oh yeah, constant 17. Yeah. I didn't know it was on the calculator. I was looking at the formula book. Constant 17. Lastly is to balance this equation. 2, 3, 2, 90 thorium plus a neutron becomes an isotope of thorium plus, what the heck? But it says there's a beta going on, but they didn't fully write it in. It's a bit messy. Right, anyways, we know what a neutron is. What's a neutron? It's 1 here and 0 here. And that decays into thorium. But they don't say if it's an alpha or a beta, but anyways, it would have to be here 2.
No, do the other two first, and you do the thorium last.
But it says that beta's here, right? But where's the electron? It's not in the diagram. So should I write it in? I think I should.
Beta is minus 1, yes?
Yeah, what's happening here is a neutron is fired at a thorium, and then it attaches to the thorium. So you get 2, 3, 3, 90 thorium. Okay, so that's fine. The neutron just sticks on, and then it undergoes a beta decay and becomes something different, plus an electron, which is 0 minus 1e, isn't it? I need more space actually. Right, so what number must be here? It must be 2, 3, 3. No, try again. Very good. And then after that, it beta decays again into uranium, plus another beta here. So this one here must be 92, and this one here will be 2, 3, 3. Now we know if we did this right because uranium should have 92 protons, but we don't have a periodic table. But I can see in the marking scheme I am correct. Which actually, you know, that's 4 marks for completing that.
In the marking scheme, he mentioned electron.
No, he didn't actually. He just left it without the electron drawn in. I don't know why. I should really. You see how I don't know. Right. So that's number 4. Okay. Yes? You doing okay there? Too much monster drink? Give me a heart attack? Can I close this now? Yeah? I think so.